Okay, folks, we're talking about kind of the second concept here in our kind of grab bag chapter at the end of the year. This is where we're talking about repeating decimals as fractions. So kind of really no new vocabulary here. Our objective is I can write repeating decimals as fractions. So got a word problem here. Sort of easy access to a highlighter. Gio's batting average for his baseball team last year was 0.556. Batting average is the player's total hits divided by the total number at bats, right? So that's kind of how you calculate that percentage or that statistic. So what is Gio's batting average as a fraction? That's the question. Really no important information beyond this because you guys don't know how to do this yet, right? So we gotta, it's kind of a new way to talk about this kind of stuff, right? 0.556, the idea here with that 6 at the end is that it's rounded up from 0.555555. So it's 0.5 repeating, right? That's generally how baseball averages work. They typically round it to 3 digits, okay? But this is not the actual precise one because it's 0.5 repeating. So the idea here is that you're gonna set your repeating decimal equal to x, okay? And I'm just gonna go out a few, right? And we realize that this means that it goes on forever with 5s, right? And the idea is that you're gonna kind of set up a subtraction problem by multiplying both sides by 10 to the power of x, okay? Now that x is how many repeating digits there are. Okay. Now in this one, it's one repeating digit. So this is 10 to the power of 1, which is 10. So we're going to multiply each side by 10. So what's going to happen here is that x times 10 is 10x. And then 0.5 repeating times 10 is just going to move the decimal over to the right by 1. So it becomes 5.5 repeating. And again, this goes on forever, but we don't need to write that out infinitely. And what we're going to do is subtract these, right? 10x minus 1x is 9x, okay? And then when we subtract it here, you just realize that these are just going to cross each other out, and that you get to 5 minus 0, and you get to 5, okay? So then we've got a very simple equation at this point. We just divide by 9 on both sides, and we get to x equals 5/9. So the summary here is Gio's batting average as a fraction is 5/9. Okay. So now we've got a couple practice problems. I will go through these, but you should probably try to attempt these on your own before you kind of come through and look at the explanation for it, okay? But the idea here is it's going to be the same thing, right? You're going to multiply, sorry, my bad, x equals 0.7 repeating, and then you're going to multiply it by 10, right, on each side. So it's going to be 10x is equal to 7.777. Remember that all that happens when you multiply this by 10 is that it moves the decimal over by 1 to the right. So now we're going to subtract. These cancel out to 0, and then we get 7 right here, and this becomes 9x equals 7. You divide by 9, then we get to x equals 7/9. Okay? We're going to do the same here. My write small for this, just because I didn't give you guys a lot of room here. 0.33. This becomes 3.33. As we subtract, those cancel to get to 9x equals 3. We're going to divide by that 9. We get x equals 3/9, which you should hopefully realize if you divide the top and the bottom by 3 to simplify the fraction. Can you see yellow right there? You divide by 3, you get to 1/3. Okay, now what you should start kind of realizing here is that there is a pattern to this, right? So I don't really even need to do this because I know it's going to be 8/9. So what is there a pattern that you notice? Yes, the fraction has a denominator of 9, or the fractions have denominators of 9. Okay, and we're going to kind of use that to kind of speed things up when we actually talk about practice or the test. But for right now, we're kind of going to go through the math of all this for this one, right? But we've done 3 examples, kind of like the proper in quotes, the proper way to figure that out and show you the math. But in reality, it's the shortcut is just you put it over 9. Okay, it does get a little weird when you have kind of like non-standard problems, right? Sabine entered a division expression into her calculator. Here, the quotient is shown on the calculator screen. What expression could Sabine have entered? So the idea is that this is going to be x equals 0.2 with a 6 repeating, right? So we have repeating decimals with non-repeating digits. So this 2 is not repeating, but this 6 is repeating. So again, just like this, we have 1 repeating digit, so we're going to multiply each side by 10. So again, this becomes 10x here, but this becomes 2.6 repeating, right? Okay. So now when we subtract, we cancel out here. This becomes 6 minus 2 is 4. We carry the decimal down. 2 minus 0 is 2. And this is still 9x right here. So it still follows that same pattern of getting that like 9x on the left side, but it gets a little weirder at the end because we end up with x equals 2.4 over 9. And just like we don't want negative exponents in your final answer, we want positive exponents, we don't want decimals in a fraction. So we can get rid of that by multiplying the top and the bottom by 10, because that's just going to move the decimal on the top to the right, kind of like what we saw happening in all these, right? Multiplying by 10 just moves the decimal over. And if you multiply the top and the bottom, it's the exact same thing. So we end up with x equals 24/90ths, okay? And then we're going to simplify. Well, let's see, it's going to be divide by 2 on the top and the bottom, and then divide by 6. Yeah, we can divide by 6, I think, on the top and the bottom, okay? That's going to get us 4 15ths, right? Yep. Okay, so she could have entered, because it is a word problem, right? 4 15ths. Let's see if that actually does it on our calculator. 4 divided by 15. Yeah, boom, look at that. Okay, so if we enter 4 15ths on the calculator, we get the exact same thing right there, okay? Now we've got 2 problems like this. Again, it's not as straightforward as when you have 1 repeating digit and nothing else, right? Because you can just put it over 9 and be done with it. This one you'd be like, oh, just put it over 90 and be done with it. But remember, right, this is 24 versus 26, or 2.6, right? And the reason is because you have that extra 2 in there that's not repeating. So this becomes x equals 0.37. And then we'll multiply by 10 on both sides. We get 10x equals 3.77. So then we subtract to get to 9x. Those cancel. 7 minus 3 is 4. That. And so we've got 9x equals 3.4. We divide by 9 to get to x equals 3.49. And then, because we don't want decimals in our fraction, we multiply the top and the bottom by 10. If we do it on the top and the bottom, that maintains kind of like the integrity of the problem. So we get to 34/90ths, and we'll want to simplify that. We'll just divide the top and the bottom by 2, and we'll end up getting 17/45ths. Okay. So it's not as simple as these, obviously, because you can just plop these over 9, right? But these are kind of the steps to do it, right? So we end up do the same thing right here. We've got 5.44. We'll just go out twice. We get 10x equals. Oh, my bad. I'm going to start over here because I screwed that up. So 10x equals 5.44 on top, and then x equals 0.54 on the bottom. So we subtract, cancel those out. This gets us 9x, and then we'll have to borrow here. So 14 minus 5 is 9, and then 4. So it's 9x equals 49, or 4.9. We divide by 9. X equals 4.9 ninths. Multiply by 10, and we get 49/90ths. Is the pattern you notice? I'm like, yes, the denominator is a 90. The denominator is 90. Okay, for these particular problems, okay? Now we get to here, we got right repeating decimals with multiple repeating digits as fractions. So we've got 2.09 here. We're going to write this as a mixed number with a whole number and then a fraction with it. So in the first example, we saw that we're actually multiplying both sides by 10 to the power of x, where x is the number of repeating digits, right? In the previous two, we only had one digit that was repeating, right? So that's 6 in this one. So we multiplied by 10 to the power of 1, which is 10. Now this one, we have 2 repeating digits, so our x value is 2, so this becomes 10 squared, which is 100. So we will be multiplying both sides by 100 rather than by 10. Now, when it has a whole number out front, I kind of like to get rid of that whole number and add it in the end. The problem is you just got to remember to add it in the end, right? It's way easier when you do that. So I'm just going to forget that whole number for a moment, and I've got x equals 0.0909, right? And on the top, I'm going to have 100x, right? Because we're multiplying by 100 because it's 10 squared. And so this is going to move the decimal twice over. So this becomes 9.0909. And again, that goes on forever, right? So it's 090909. So we subtract and we get 99x here equals 9. Okay? So we divide by 99. We get x equals 9/99, which we can divide the top and the bottom by 9. And we get x equals 1/11. But don't forget, add that 2 down at the end, right? So x equals 2 and 1/11, okay? Okay. Similar right here, just a couple practice problems. Hopefully you should already kind of like be getting the pattern, right? The idea is that it's going to be over 99, right? When we have 2 digits, okay? So this is going to be x equals 0.3434, and then 100x equals 34.3434. And again, goes on forever, right? But we don't need to do that because it's just going to get eliminated. So this becomes, as we subtract it, 99x equals 34. We divide by 99 on both sides, and we get x equals 34/99. And I think that's going to stay as it is. You can divide by 2, you can divide by 17, and neither of those is going to go into 99. So that's our kind of final answer there. Again, when you have a whole number out front, just forget about it until the end and then add it back in. This becomes 0.2727, again, goes on forever, and then 100x equals 27 point, gotta make sure you line your decimals up, otherwise this is gonna screw you up, 27, okay? So this becomes 99x equals 27. We'll divide by 99, okay? We'll divide by 9 on the top and bottom. So this becomes, divide by 9, 3/11. And then don't forget your whole number. So 4 and 3/11. Okay. Is there a pattern you notice? Yes. The denominator is 99. Okay. One of the two equations is a system of linear equations, or one of the two linear equations is a system of linear equations as given below. Gosh, that's terrible. One of the two equations in a system of linear equations is given below. There you go. Okay. Provide a second linear equation that would cause the system to have no solutions, right? So no solutions, remember, would be lines that don't cross, would be parallel. So the idea here is that you would want to keep the same slope, but have a different y-intercept. So for the first one, it's got to have that same slope, but literally any other number would do it, okay? And so then explain why. This system would have no solutions. because it would have the same slope but different y-intercepts. So the lines are parallel. So the lines are parallel. Okay. Provide a second linear equation that would cause the system to have exactly one solution. So that would mean that the lines would cross once. Oh, you know what? Before we move on, I do want to show you what that looks like. Right? So if we take that first one, it's y equals 5/6 x plus 7/9. That's our line right there. And then if we do the second one, 5/6 x, and I said minus 11. We'll have to zoom out of it. You can see that these lines are parallel. They're not going to touch, but they do have the same slope, right? That 5/6, right? Okay. So now the second one, we have exactly one solution. So the idea here is that you need to change your slope to a different number. You can have the same y-intercept, or you could have a different y-intercept, but the important thing is that you have a different slope. So we could say y equals, I don't know, again, doesn't matter. We could even keep the same y-intercept, okay? And the reason this system would have one solution because a different slope means the lines cross once. Cross exactly once. Okay. So if we see that, I've got the first one right there. We'll zoom in a bit. So I'm going to change it to, what did I say, y equals 3x? Yeah, y equals 3x plus 7/9. Same y-intercepts, they cross at the same point right here, but they have different slopes. One is steeper, one is less steep, so they cross once. So that's the idea there, folks. There you go.